For this family of functions question, what we have here is a particular rule, and we're going to answer a whole heap of questions based on this rule here. So we can tell that we've got a cubic function here. A and B are positive constants with B larger than A. Alright, so if we kind of imagine the graph of this, then we've got B here, maybe A here, could be anywhere along here. We know that this is a stationary point as well, so that means that we're going to turn over here and we're going to go like that. Okay, so this is what we know that this family looks like, and depending on the value of A and B, the graph will just change. So there's nothing to say that A and B are positive constants, so that's good to know. Yep, so it is going to look like this. Alright, so we're going to do the first part, which says find the derivative of f with respect to x. So let's jump on CAS. F of x equals, it is x take a all squared times x take b. Okay, and let's do a shift subtract d dx f of x. Alright, so we've got f dash x equal x take a, 3x take a take 2b. Alright, so there's our derivative. We could also write that in expanded form if we want. Expand ants. Nah, that's not. Okay, so find the coordinates of the stationary points of f. Okay, so this is part B. So what we need to do is we need to get the coordinates of this and this. Alright, so we already know this stationary point is going to happen at a comma 0. So we don't need that one. We don't need calculus for that. But let's do f dash x equal 0 and find out where the other one is. So we'll go and... So this is the derivative here. So we'll go zeros, ants, comma x. And it says it's got two stationary points, one at A and one at A plus 2B on 3. Right, so we've already got the A comma 0, we know that one. So we're going to get the other one by noting that the x value is A plus 2B over 3, comma. And all we'll do is just feed this f of a and s. It's going to be 4 a take b cubed over 27. So there are two stationary points. Alright, show that the stationary point at a comma 0 is always a local max. Alright, so the way we typically do these ones here is that we need to basically use a gradient table. So we're going to show using a gradient table because you can't sort of just go look at graph, clearly local max. So what we need to do is sub in some values. So the way we're going to set this up is we'll go and write a table like this where we've got a value that we're going to use for x and two values on either side. And what we'll do is note that the value for x in this case is going to be, so our value here is going to be a, we need a value less than a, which is going to be 0. We need a value greater than a, but we also need to make sure that that value is between a and whatever the stationary point is as well. So we need a value somewhere between here. So I'm going to hold off on that just for the moment. Okay. Now what we're going to do with those values of x is put them into f dash x to find out what the gradient is at that point. And then what we're going to do is note the shape. Okay, the shape. Okay, so we know that at 0, the shape f dash x is going to be over here. What we're going to get is a positive gradient here. So it's going to take this shape. At a itself, it's going to be 0, and between a and whatever this value here is, well, it's actually this value, then we know that it's going to be negative, okay, because we've got a negative gradient over here. And this will, again, allow us to conclude that it is always a local max. It will never change. Okay, so let's go ahead and do that. So the first thing I think we do is we grab the gradient function and we go, what are you with x equal 0? And it says that the gradient is a squared plus 2ab. Okay, now how do I know that that's positive? Well, again, what we're going to note with this is that if a greater than 0 and b greater than 0, then a squared plus 2ab also has to be greater than 0, because you can see here you're adding a positive number to a positive number, which is going to be positive. All right, so that is the conclusion that we'll make. All right, now going back to the derivative, we'll put in x equals a. I know that this one's going to be 0. Okay, so that's 0 gradient there, which means that we've got this stationary point here. All right, so this point here, well, what we need to do is work out the point at this time. So the way to do that, to work out a value that's in the middle of this, which is a, and this point here, which is a plus 2b on 3, that's what that point is there. What we'll do is just basically get the average of those 2 points. Now, if we get the average of those 2 points, it's going to give me a value that sits in the middle. Okay, now you don't have to get the middle point, but this just guarantees that the point that we're using is indeed in the middle. All right, so we're going to go a plus 2b on 3, and then we're going to divide that result by 2. Okay, and that'll give us the x value of a point between the middle of this stationary point and this stationary point. Okay. All right, so let's just do that on the calculator. A plus 2b. I'll use some fraction signs. A plus a plus 2b over 3. So that's that. Divided by 2 is that. So the x value we're going to use is 2a plus b on 3. All right, so essentially what we're going to do is now put that into the derivative function. So we get that. Can I simplify that at all? I think if I get a common denominator, I think there's fraction, common denom adds. It's not much better, but anyway, let's write it down. Negative a squared plus 2ab take away b squared over 3. I wonder if that top line can be factored. Grab you, chuck you there. Yeah, okay. Now let's write that down. Okay, so you can see the calculator won't automatically simplify it, which is a bit of a pain. Sometimes you end up writing something down that just can be written much easier. So this is negative a take away b squared over 2. All right, and so what we know is that actually is a negative number, and the reason we know that is if so we know that if a is greater than 0 and b is greater than 0, then a take b all squared is greater than 0. All right, so this is enough to make the conclusion. Actually, you don't need a further so. right? Because what that means is if this is greater than 0, so a take b all squared is greater than 0, then whatever that value is, it's positive, it gets negated, all right, which makes it a negative number, and then halved, which is still negative. So that's enough to conclude that this is a negative number, okay? So this is enough now for us to conclude that, therefore, it's always a local max, okay? So we can say here, therefore, always local max. All right. D. Find the values of A and B if the stationary points occur where x equals 3 and x equals 4. All right. Well, the first thing I know is A. This value here, A, has to be 3. And the reason I know that is that the A value, the B value is greater than the A value. So given that the A value occurs first, this is the lower number, it has to be 3. Right, so the other one is going to occur when x equals 4. So I know that the stationary point occurs for this particular x value, okay, a plus 2b on 3. Is when the stationary point occurs, okay? And that, I know, the stationary point is equal to 4. So what does b have to be? Well, I've got a plus 2b equals 12. I know that a is equal to 3, so I've got 2b equals 9, b equals 9 on 2. So there's my value of b and a that will make this happen. So there we go. There's a families of function question, and yeah, it's a pretty tough one, I have to say, conceptually. Common mistake students make is probably when they select a value to the right of A, they select any other value. So they might select B, or the halfway point of A and B, which could be here, could be here, depends on the values of A and B. So the technique I showed you, which is the halfway point of the stationary point and this zero gradient point, is probably your best method. Alright, let's finish this off with the last few VCAA questions over here. Okay, so this first one, let f be a function with a domain is the set of all real numbers such that f-5 equals 0. So what that basically means is, again, if we were to draw one of these diagrams here, we've got the values of x that we're going to choose, which is 5, f-x and shape. We can now make a conclusion on what we're going to look like. So f-5 is 0, which means it goes like this. And this is basically saying when x isn't 5, so when it's 0 or when it's 10, what we've got is a gradient that's less than 0, i.e. negative. Okay, so negative gradients look like that. All right, so our shape is going to be like this, which means that basically we've got a graph that does this. Okay, which means that it is a stationary point of inflection. This question here involves the classic open top box style question. So what we've got in this case here is Zoe has a rectangular piece of cardboard, 6 by 8, and what she wants to do is cut these side lengths out to make this open top box. So what she cuts out, we're going to write down, that's going to be x. Okay, and therefore she'll end up creating a box, x height, 8 take 2x length, and 6 take 2x width. So our volume, V of x, is going to be just x, 6 take 2x, 8 take 2x. Now, in this case here, we can see that we're going to get 2x intercepts over here, so the function is going to go like this. So what we're doing is v versus x, we want to get this stationary point value here. So the value of x for which the box is at a maximum is closest to. So let's quickly knock this one out on the calculator by defining it first. Don't have to define it. diff it. And then we'll run, what do we want to do? Solve f of x equals 0 for x. So I won't use zeros, I'll use solve. And I'm going to get a decimal approximation. Solve f of x equals 0. That was smart. Solve the derivative, please. This thing. Equals 0 for x. Two values. We want the first one because the next one is a local min. So that's going to be 1.13. So 1.1. There it is right there. Okay, so the classic trapezium. So we've already seen this one. The sides A, B, AC are of equal length. So AB and BC is this one, and DA is this one. So this again is an isos trap. All right, and again to note that isosceles trapeziums are maximized when you form the trapezium out of 3 equilateral triangles. Okay, so that is going to go to there, that is going to go to there, and these are going to be equilateral triangles. So the area that when the trapezium is a maximum is going to be, so we know that has to be pi on, so it has to be 60 degrees or pi on 3. Okay, pi on 3, pi on 3. So we can just write the answer down, it's just D. Right, so as long as you know that that's the case, but again, if you want to work that out mathematically, you need to go back to where we did that question earlier, which involved that. Right, so it's basically the exact same question. This one though, I suppose it's a little different in the sense that it says that what is the maximum area. That one does. This one just says what's the angle it's going to create the maximum value. Okay, for this function, the average rate of change with respect to x over the interval is, so a bit bizarre that this question's in here, but doesn't really have anything to do with this. So define f of x equals sine of 2 times pi times x plus 2x. So all we'll do is go control divide. So the interval's f of 5, take away f of a quarter. So y2 take y1 over 5 take away a quarter. There we go. All right, part of the graph of a function is here. The first 3 turning points are labelled T1, T2, T3. The x-coordinate of T3. All right, so I think what we'll do for this one is we'll get a derivative. So we'll go f dash x equals 0. And what that's going to do, that's going to give us a general solution. So essentially what we'll do is just start stretching out the domain far enough that it produces 3 solutions or 3 stationary points. And once it does, we'll be able to get the third stationary point in the list, which will correspond to this particular x value here. So let's try it. Define f of x equals e to the, what is it going to be? Yeah, root 3 sine, or x times root 3. Control root. X times root 3 times sine x. Yeah. Alright, so let's get our derivative. Shift minus d dx f of x. Now we'll go solve, ants equals 0 for x. Now again, just to note that I can't just ask this question here because it gives us a general solution. Well, I could use the general solution. It's actually going to be 3 lots of this, but it's probably going to be easier if we just give it the domain. So 0 less than x less than, and I'm just guessing, pi on 2. So I'm just going, I don't know, is that enough? Well, it doesn't. So it doesn't go stationary there. So let's just stretch it out. 2 pi maybe. Okay, we've got 2 solutions. And then all we'll do is just stretch it out to 4 pi and see what happens. So first, second, third, 17 pi on 6. So there it is there. So you could have used the general solution that we got up here and just multiplied that by 3. So n would be 3 lots of this. But it's a bit easier if you just do it the other way. It takes on this form here. We know something about A, B, and C is that they're positive. And what we want to know is when is it not going to have any stationary points? Okay, so again, the interesting thing about cubics is people assume that they always have stationary points, but this is one that goes like this, where what we have is a point of inflection that's not a stationary point of inflection. Okay. So the way we'll do this one is we'll go f dash x equals 3ax squared take away 2bx plus c. Alright, now this is our gradient function, and what we want is the gradient function to be, we want the discriminant of this to be less than 0, so it has no solutions. Okay, so what we'll do is we'll go discriminant is b squared, which is going to be 4b squared, take away 4 times 3a times c. That's the discriminant is 4b squared, take away 12ac. Now 4b squared, take away 12ac, we want that to be less than 0 for no solutions to the gradient function. So let's go solve 4b squared, take away 12a times c, less than 0. We want to solve that for c because we can see all the solutions here are given in terms of b and a. And let's see what happens. So we get 2 possibilities. So there's this one when a is greater than 0, this one when a is less than 0. Now we know that a is a positive constant, so it has to be this one here. So it's the first solution. So that's b squared. It's this one here, I think. Yeah, this one here. So it's got to be d. So there you have it. Right, so the resulting homework is going to be to do 10G. Okay, so do those questions.